An electric circuit is a complete path for current to flow from the negative terminal of the power supply through the components and back to the positive terminal of the power supply. One type of circuit is called a parallel circuit. This is an electric circuit with more than one path for the current to flow. That means the components can be connected on different branches, just like you see in the diagram below. There's the shorter path right here. The electrons can also take the longer path and go through the second light bulb like this. Electricians use schematic diagrams because everyone draws differently. Let's use those universal symbols. We have a power supply and a wire running to a light bulb, to a switch, back to the power supply, completing the first path. We have a second path with a light bulb on it, also going back to the power supply. First, let's build a parallel circuit using the simulation. We'll have a power supply set to 6 volts. We have a switch running to a wire and a bulb, and back to the power supply. We can add a second branch or path over here. There are now 2 paths back to the power supply, the long path and the short path. With the switch closed, there's a complete path and electrons can flow. If the circuit is open, or if a wire is disconnected, electrons will no longer flow. But if you disconnect a wire on only that branch goes out. If a light bulb is disconnected, only that branch goes out. The other one still has a complete path, and electrons will flow. We'll begin by lighting a light bulb. We need a switch and a wire running to the bulb and back to the power supply. We want both bulbs to light up on their own. We need 2 separate paths. Short path right here and the longer path over here. We can make each path a different color, starting with green. The shorter path will run a green wire to the bulb and to the bulb back to the power supply. That path works. Now we'll add in another path using yellow wire. We have an intersection right here running to the bulb and back to an intersection over here. Now we have 2 complete paths, the short green path and the longer yellow path. We have a master switch that controls everything because it's before the split. If I disconnect this wire right here, both bulbs go out because again, there's no complete path. Each path can work independently. If the bulb goes out, or a wire is disconnected on the green path, the yellow path stays on because it still has a complete path. Same thing with the yellow. Bulb goes out, or wire is disconnected, the green path still works because there's still a path back to the power supply. If a wire is disconnected after they return back together, then nothing works. There's no complete path. We use a voltmeter to measure the voltage across a component. We place the red wire closer to the positive side of the power supply. We can see the voltage from the power supply is 6 volts. The voltage across the first light bulb is also 6 volts, and the voltage across the second light bulb is also 6 volts. Let's use our multimeter to check the voltage. The voltage across the first light bulb is about 5.3 volts. Across the second light bulb is right around 5 volts. Across both light bulbs is again right around 5 volts. So the voltage is not changing when the circuit's wired in parallel. We can use an ammeter to test the current. That's how fast electrons are flowing through the wires. In this circuit, the current is 0.8 amps before the split. After the split, the current drops to 0.4 amps on each of the branches. After they come back together, the current is added together back to 0.8 amps. We can check this in our circuit by setting the multimeter to read current. We put the wire in line with the bulb. The current through the first bulb is 0.13 amps. The current through the second bulb is 0.14 amps. The current on the main path, that's both path 1 and path 2, is 0.27 amps. Notice 0.13 plus 0.14 is 0.27. The current through the main path before the split was the two currents on each path added together. And that is the same as the main path going back to the power supply. This is also reading 0.27 amps. Right now, this circuit has a master switch. If we add a switch along each branch, then that switch will control only that branch. Let's add some bulbs and see how it affects the brightness. Now we have a master switch that controls everything, and a switch on each branch that controls only that bulb. If a bulb is removed, only that branch goes out. The other ones will remain lit. Let's do the same thing on this circuit. We have a master switch, but a light bulb that controls just the green path needs to be on just the green path. We'll hook a switch into the green path, and that will control just the green bulb. We can do the same thing on the yellow path. Put a switch on just the yellow path, and that will control only the yellow path. Now we have a master switch and a switch that controls each branch individually. We can use the same process to add a third bulb in parallel. Here we have the white path with its own switch. So each branch now works independently, and the master switch controls everything. Now let's measure voltage using our voltmeter. The voltage of the power supply is 6 volts. The voltage across each bulb is also 6 volts. Let's set our multimeter to measure voltage. The power supply is applying 6 volts. The voltage across the first bulb is 5.6 volts. Across the second bulb, it's about 5.7 volts, and the third bulb is about 5.6 volts. The voltage across each bulb remains the same. Let's see if that holds for the current. The current through the wire on the main path is 1.2 amps. Path 1 is reading 0.4 amps. If we subtract 0.4, on the remaining path we now have 0.8 amps. If path 2 is also 0.4, then 0.8 minus 0.4 leaves path 3 with 0.4 amps. After they come back together, paths 2 and 3 combine to 0.8 amps, and then 1, 2, and 3 together are back up to 1.2 amps. We can check the current in this circuit by setting our multimeter to measure current. The current in path 3 is 0.13 amps. The current in path 2 is also 0.13, as well as path 1. Combined, 0.13 plus 0.13 plus 0.13 is 0.39 amps. The main path has a current of 0.4 amps. So in this parallel circuit, the voltage was remaining around 6 volts, but the current was increasing every time you added a path. Now let's increase the voltage from 6 volts to 12 volts. The current has increased everywhere in the circuit. The electrons are moving very fast, and the bulbs are getting much brighter. On our circuit, let's increase the voltage to 9 volts and 12 volts. You can see that's increasing the brightness. Let's use our multimeter to measure the current in each wire. The current through path 3 is 0.13 amps. If we increase the voltage, the bulbs get brighter, and the current through the wires is increasing. Now let's use our multimeter to check the voltage. the voltage across the bulb is about 5.7 volts. Increasing up to 12 volts in the power supply increases the brightness. Now the voltage across the bulb is about 11.7 volts. To sum everything up, parallel circuits have many advantages. First, you can control individual components, so it's easier to troubleshoot. If one component goes out, the others stay on, because there is still more than one path. Adding more components doesn't reduce the current, so adding bulbs doesn't reduce the brightness. There are, however, some disadvantages. A parallel circuit is more difficult to design and build, it uses a lot of wire, and there's a higher risk of overheating and blowing a fuse or a circuit breaker, or causing a fire, because as you add more branches, the current increases through that main path.